So imagine I have two charge planes. One is here, one is here. They're a little distance apart. Okay, some distance d apart. So this is charge plus q, this is charge minus q. What was that formula I wrote down for the electric field of a charge plane? I said it's going to be on either side, it's going to be q over 2 times a times epsilon naught, where a is the area of the plane. So imagine these planes are actually extending in this direction. So you have two plates facing each other. So each has some area A. Now what I want to do is figure out, if I put both of these together, what will be the net electric field. So let me do one at a time. Which way will the electric field of the positively charged plane point? Away from it on either side. So that's the field of the positively charged plane. But you see that continues, that's not just next to the plane, it keeps going in that direction. The field of the positively charged plane is going to be everywhere to the right hand side of the positively charged plane. Remember, it's constant everywhere, and it will keep going on this side as well. Okay, so far I've only done the field of the positively charged plane. How would this work if I were calculating now only the field of the negatively charged plane? So far these arrows I've drawn are only due to the positively charged plane. If I were to draw a similar set of arrows for the negatively charged plane, how would they be different? They would go inwards towards the negatively charged plane, but the length of the vectors would be the same, right? And I should draw those everywhere, both to the right and to the left of the negatively charged plane. But on both sides, they should be pointing towards the negatively charged plane. So let me put those in a staggered fashion. Maybe I make it dotted lines. Here I'm using superposition to say, if I were drawing the field of the negatively charged plane, it would be pointing towards the plane everywhere on the left. But on the right, it's pointing towards the plane, so I would have to draw them this way. If you look at these vectors, I can pair every vector of the positively charged plane with one of the negatively charged plane and cancel them out. You can do that because it's independent of the distance, exactly. Because it's independent of the distance, all these vectors are the same length. So at every point in space, what you're saying is if I'm outside the plates, the field due to the negatively charged plate is going to point this way. The field due to the positively charged plate is going to point the opposite way, and they'll have the same magnitude because it doesn't matter that I'm closer to the negative plane and further away from the positive plane. So everywhere on this side, there's no field. Everywhere on this side, there's no field. What would be the magnitude of the field in between? If this is the field due to one plane, what will be the magnitude of the field now between the planes? Double that, exactly. I just take that value, multiply it by 2. So what that does is just get rid of that 2 over there. Okay, so they add up between the planes. So in between the planes, I'm going to have E is equal to Q over A times epsilon naught. And outside, what will it be? So if you wanted to look at the electric field pattern of a pair of charged plates, so let's say this is positive, this is negative, what I'm going to get is electric field lines that look like this. Now, of course, in real life, you don't have infinite planes, so how does this get modified? It turns out that there's a little bit of fringing here. You'll get field lines that look like this, but no field lines near the planes on this side. So here E is equal to 0, here E equals 0. Okay, so this arrangement is called a capacitor. And so the field between a capacitor, between the plates of a capacitor depends on how much charge I've put. So I've put plus Q on one and negative Q on the other. So I have equal and opposite charge. I don't know if you realize this, but this looks a lot like a dipole where I've extended the region where the positive charge is distributed and the negative charge is distributed. The field lines will look a lot like that of a dipole as well. So this particular arrangement is called a parallel plate capacitor. For obvious reasons, the plates are parallel to one another, right? Because these are plates where the extent of the plate is going into the screen. And you know that the electric field between the plates is constant and depends on the area of the plates and the charge you put on the plates. So what a capacitor is basically is a charge storage device. It's a way of storing charge. So I can put charge on this, okay, and create an electric field in a region like this.